which what goes in goes in. Now, what they do with something like this is they put a bunch of them in a row. I'll just use 4 for this particular example. And the output of here becomes the clock signal, the next one. So this one will divide by 2. This one will divide by 2 again, which will be like dividing by 4, by 8, by 16. So for every 16 pulses you put in here, you'll get 1 transition here. Divide by 16 counter. Now what you can do is you can pull certain outputs here. You can take the positive output out of this guy, you can take the negative output out of this guy, the positive output of this guy. Basically, if you're looking for a particular number, you can count up to that point and stop counting. Or you can take all 4 outputs and you can put them to one big NAND gate, and you'll get 16 pulses in, and then you'll get 1 pulse out. Basically, they'll be divided by 16 counter, or if you grab certain interior outputs, it'll be divided by something smaller number. These are the basic dividers in computers. I'm trying to think of what other basic things I can talk about. I was going to talk about an adder, and I forgot how you do that. You use an AND gate and an OR gate together, and they produce the logic of an adder. So A is your input and B is your second input. The C output will be A plus B. And you can gang these things together, and that's how the computer does addition. So you can do counting, you can do storage, you can do a whole bunch of what-if things. You can do sampling too. Another thing about this is, let's give you one other example before I move on to the next subject. You can do serial to parallel conversion using those devices. I'll give you an example. We'll take our JK flip-flop, and this time we'll make it with all the usual connections. And you got the clock here. And all these clocks are connected together. And here's you got a stream of information coming in here. And then there's a sampling thing here. So basically, your clock is going to have it occur somewhere in the middle of that period when you want to see what the value is, whether it's a 1 or a 0 at a given point. And what you're going to get is the stream of pulses here that's coming in here. It doesn't always happen to be a square wave. It could, stay 1 for a couple steps. When you put the clock through it, it's going to ripple this thing through. So this thing will have a binary value equal to what the stream of serial information look like. You're putting information in serially, you're taking it out in parallel. And think about, the fact that we had interfaces to our printers that were parallel, Centronics 101 interface. We had newer interfaces, RS-232, that are serial, where you only need 2 wires to transmit and receive, plus the common return to send the information, plus some flow control if you wanted to have clear to send, request to send type of stuff, and data terminal ready, data set ready, that kind of stuff. That's what you can build with these building blocks. I'm not going to go further because it's not on the test that we do anything fancier than that, but when you take basic RS flip-flops and you gang them up and you clock them and use sampling time periods, you can basically use memory, you can convert serial to parallel, you can have a ring counter that says I'm going to produce a pulse any subset of the number of times the incoming pulses come through. You can do addition and subtraction, you can do all the components of what a computer does. You can move data around, you can store it in interior places temporarily in what they call registers. You can do addition on it, and then you can do all these logical what-if functions. And the what-if functions are, okay, I'm gonna tie this thing to a sampling line. Whatever value is here, if this thing goes 1, we'll end up over here. If this is 0, then it'll be a 0 over here. Whenever this thing turns on as a 1, it becomes a sampling device. It's a gate. It captures here what's available at the time when this guy decides to do the sampling process. All right? I want to spend a little time on our favorite misunderstood subject, the, what's it called? Decibel. Decibels are sort of like what we talked about earlier. They are powers of numbers used to their fullest advantage. If I want to multiply, I have to switch back to a non-black color. If you wanted to, can't use that one either. Let's go back a little. If you wanted to multiply 10 times 100, knowing that 10 is equal to 10 to the first power, 100 is 10 squared. If you just add up those exponents and you get 10 to the third power, that's 1 followed by 3 zeros for third power. 10 times 100 is 1,000. You can do multiplication by doing addition if you use the exponents. Take it a step further. 10,000 is 10 to the fifth. There's 10 to the fourth. There's 4 zeros there. Multiply these two numbers, and you get 10 to the sixth, which is a million. 6 zeros. And isn't that true? 10,000 times 10 is 100,000, times 10 again is a million. Just add the exponents, and you get the result. Well, a guy somewhere in the history of mathematics figured out that, well, you know, this could be useful for some things. So he came up with a table of logarithms. Logarithms are the exponents of values of numbers. So if you had a 5-place logarithm, for 1, the logarithm would be 0. For 10, the logarithm would be 1. For 100, the logarithm would be 2, and so on. What about numbers in between? Is 15 something that has a logarithm? It's in between 10 and 100. Let's say 50. Let's say the number 50. So what's 50? It should have it should be 1 point something, right? So I'm going to take 50, and take the base 10 log of it, and it happens to be 1.69897. It's something between 1 and 2. Let's try something here. Let's multiply this by 2. Okay, so it's 3.39794. Let's take the anti-log. The number is going to be, let's go up one step further. If this is the logarithm, we're going to get it, and we turn the process backwards, we're going to have a number between 1,000 and 10,000. What would that number be? Well, here's what I'm going to do. I'm going to raise 10 to that power. Let's see what I get. And the number I get is 2,500. Well, guess what? 50 squared Oops, excuse me, I gotta try that again. Hit the wrong button. 50 squared, where's the square button here? There it is. It's 2,500. So when I multiply rather than add, it's like taking a power. You get a lot of shorthand things out of this. When slide rules existed, the way they worked is they had the numbers from 0 to 9 laid out logarithmically. What you're really doing is, if you took the C scale and moved it over, so it's the number you're looking for is on top of the D scale, you're taking the logarithm of C, the logarithm of D, and you're adding them together, which is multiplying. And what you would get is the product. With the slide rule, you did not add, you did not subtract. You could multiply, you could divide, and you could take powers, and you could take roots, because that's what the exponents do for you. So, voila, there you have it. Okay, what does it have to do with logarithms? Well, I should say, what does it have to do with decimals? A bell, which is actually named after Alexander Graham, is the logarithm based on 10. There's other bases like natural logarithms, which come out of trigonometry when you take that course. But if you're looking at powers of 10, a bell is the exponent of this ratio. In other words, if this is twice that, it's whatever exponent equals 2 happens to be. Well, one thing for sure is it will produce a number that's less than 1. And people didn't want to deal with fractions, so they added a multiplier. They called it a decibel. They said, let's take 10 and multiply that by the log of these ratios. All right, let's just say for the sake of argument, this is twice this. So you want to get the base 10 log of 2. What is the base 10 log of 2? Well, it's got to be about 0.3. I'll show you why I know that. I'm going to take 10. Oops, I didn't want to do that. And if I take the log of 10, I'm going to get 1. Yep, I sure do. Okay, let's take 2. Take the base 10 log of that. 0.30103. Essentially, it's 3. 0.3 rather. So the base 10 log of this guy is actually 0.3, but we're going to multiply this by 10. So if you have something that is doubled, it will be 3 dB. You will see a lot of charts, especially with antennas. Here's a polar chart of an antenna. Okay, so there's lobe here. There's a point here and there's a point here where the amplitude is half of what it is here. They call that the 3 dB point. It's half the power of the peak value, and that's where they come up with this thing. When there's a ratio change of 2, it's a 3 dB point. If it was a ratio change of 4, it would be the 6 dB point, because we're talking exponents here. Simple example, when you have an earthquake, a Richter 10 earthquake is 10 times as, well, let me try, let's not go that high. Let's say a Richter 6 earthquake, you don't get too many higher than that, is 10 times as powerful as a Richter 5, which is 10 times as powerful as a Richter 4, and so on down the scale it goes. The nature of large numbers is that if we keep track of the power of 10 that it is, it's a lot smaller numbers to deal with than the number itself. It's like having in the old days when Italy had the lira, not the euro. You know, you buy something for 10,000, 20,000, 100,000 lira. It sounds like a huge number. It might be $5. It just got to be ridiculous because they had so many inflations that they didn't want to rework their monetary system. But this is true with sound, it's true with earthquakes, it's true with a lot of things, that go through a wide dynamic range, as they say, from very small numbers to very large numbers without seemingly growing that much. So, if you buy an antenna and it's got a 20 dB gain, meaning that it's got a narrow beam so that the power goes in, but it's squeezed into a small space, and what's here is 20 dB greater than what went into that antenna. 20 dB, remember everything's multiplied by 10, is really 2 as your exponent, or 100 times greater. You get a multiplication factor of 100, you got a 20 dB gain. If you had a 10 dB gain, you'd only have a factor of 10. This is a relative measurement system, meaning it always is based on something relative to something else. And yet you hear it used in absolute terms. If you talk about sound, oh, it was so loud, the traffic noise was 90 decibels. Not 90 dB greater than some other measurement, but 90 absolute decibels. How do they do that? They have to come up with a data point, a starting point, a reference point for what 0 decibels is, and they do that. I'll give you the example of power, or I should say, especially with radio frequency power. In the radio world, arbitrarily, there's no other way to describe it, 0 dBm, they put the M there as, kind of a measurement value, is defined to be 100, excuse me, not even 100, 1 milliwatt in a 50 ohm load. 1/1000th of a watt, or 1 over. Okay, so what's a watt?